This is the maths test from 2018. I'm only doing section number 1. The first question is just the 10 multiple choice questions. I'll do the other parts at a later date. But for now, let's just run through this. So quite a convoluted question firstly. We learned from Tamura to sketch things, right? We should know what the root of x looks like. It looks a bit like a C shape like this, and then the line just has winds up to -2 down here. So we're looking for this area enclosed here, because of course it's above the x-axis as well. So just this area in here. So firstly, look for this intersection point, so set this equal to this. Now, if you're confident in just doing this without a substitution, that's great. You can just factorize this to be root x minus 2 root x plus 1, because of course root x times root x is x, minus 2 root x plus 1 root x is that, and then minus 2. If you prefer to use a substitution like this, you can do it, and you can make it into a proper quadratic, which you can put back later. But just for the essence of time, it might be best just to do this and get used to it. Of course, now I can say root x is equal to 2, or root x is equal to this, or this, I guess. Then this. Now, just be careful here. Root x is defined to be positive. So it can't be this. And of course, from our sketch, we can see that there's no other intersection here, because this is not the curve y equals plus minus root x, which would go back down here as well. It's just the curve root x, which is defined to be positive, so it does this. That's well worth just knowing when you go into this paper. This curve comes up twice in this year, so it's well worth noting what it looks like here, and whether or not it's this or y squared equals x, which comes up later and is the entire thing. So it's worth knowing the difference between those, so you don't accidentally get this intersection here. Anyway, here we get this, and then of course this, so this point is at 4. So let's integrate the curve then between 0 and 4 to find all of this area underneath it. We can do that very quickly, turn that into x to the power half, of course. I'm not going to run through this very quickly, but again, well worth being good at this kind of thing. 4 square root of this 2, cubed is 8, times 2 is 16, so that's just 16 over 3. When 0 goes in, nothing happens. So we get this, and now we can take away this triangle here, I think. I can quickly say this intersection here is when y is 0, because you're not going up or down on this line. So put in y is 0, get x is 2. This coordinate here is when you put in 4 into the line, or 4 into there, doesn't matter, you get 2. So this triangle here has area 2 times a half, and of course this area here is just all of this area under the curve. So if we take away the red triangle, we're going to get the answer, which is going to be 10 over 3. Okay, so quite a lot to do in that first question, a lot to do in the second question as well. Interesting that they expect you to know how to differentiate exponentials. So to differentiate this, the k comes down and we get k e to the kx. And then again, to differentiate again, just do the same thing. K comes down to get k squared e to the kx. This power just never changes. So that's just a rule that you need to know. So good, we've got that. Now let's put everything in. Just put everything in. Absolutely everything. And now from this bracket, we can factorize out e to the kx, but we can also factorize out from this bracket. And here I can factorize out k, and then because e to the x is not 0 ever, because exponentials are never 0, we can cancel this with this and this with this to get this. And now, if we factorize out k from that, we can get this. And now notice, I can divide this by k, this whole thing, as long as I notice that when I put k as 0 in, I get a solution. So k as 0 is a solution, and now I can divide by k to get this. And now I can look for other solutions, which are going to be 2 of them, plus minus root 2. So there are 3 solutions in total. Good. This one here, so curves have exactly 2 points of intersection. So set this equal to this, and then solve it. Rearrange to look like this. So now I can see this is in the b squared minus 4ac, which needs to be greater than 0 because I've got 2 points of intersection. This is going to be the term a, this is going to be the term b, and this is going to be the term c putting into it. I know these letters do not refer to these letters. These are just the ones that they love doing this. These are the letters we like using in the discriminant. They're not the same as these letters, which are also a, b, and c. Just be careful. So this whole thing is a. This is b, this is c. Put that into this formula here. So 0 squared minus 4 times this times that. And there's a couple of ways to do this. Well, this is obviously 0. Move all of this over to the other side, and I got this. Divide everything by 4, because I'm allowed to do that. And now, okay, so I've got 2 things multiplying to be less than 0. That means that either one of them is negative, and only one of them. So either this is negative, or this is negative. So at this point, I almost wrote down a less than b, or c less than d, something like that. But actually, none of that's here, right? Well, actually, a less than b is here, but that's not good enough, because if a was less than b, this would be negative. But if c was less than d, this would also be negative, and then 2 negatives would multiply to make a positive. So this isn't enough, and nor is this. So okay, what does this look most like? Well, it looks a lot like this, right? In fact, it looks almost identical, except for the inequality is the other way around, and this is the other way around, which is fine, because I just need to multiply by -1. If I multiply by minus 1, 0 times minus 1 is still 0. This sign flips, because when you multiply by a negative, it flips. And then I put the minus 1 here. And now just be careful. If I want to put this minus 1 into here, I only need to put it into one of them. Because like if you were doing this multiplication, you don't do 2 times 5 is 10 and 2 times 2 times 7 is 14, and then do 10 times 14. No, you just do 2 times 5 is 10, and this is the same as 10 times 7. So do this times this one to flip that one the other way around. And leave this one alone, and we end up with the exact idea there. So that was going to be the answer. Kind of interesting. This one, D, easiest thing on the paper. Not sure why it's D. Not sure why it's even here, to be honest, let alone the fourth question. Complete the square on that. Very straightforward. This is 28 over 4. So this is going to be 3 over 4 in total. This, therefore, has minimum point 5 over 2, 3/4, just by knowing how completing the square works. This graph transformation moves it 2 places to the right. So move the minimum point 2 places to the right. So leave the y coordinate alone, just add 2 to that coordinate. This is, of course, 4 over 2, added to that to make 9 over 2, and that's our new turning point. Very easy question. E, much more interesting question. When you see questions like this, you need to be brave, because you've probably never seen a question like this before. And it's tempting to think, oh, the questions that are like nothing I've ever seen before are going to be the hardest. They're actually not. As long as you're willing to think about them, they're probably the easiest, because they know you haven't seen this before, so they're not testing how good you are at stuff that you've done, they're testing how good you are at thinking things through, new things through. So this is probably not going to be that hard as long as we think it through. Circle radius 2, so that's good, centered the origin, contains, let n be a number of grid points within the circle. Now, this has radius 2, so there's a grid point here at 2, 0, which is within or on the circle. What other grid points are in it? Well, 0, 0 is, 0, 1 is clearly, and 0, 2, as I've said. Sorry, 1, 0, 2, 0, these are, aren't they? This is 0, 1, 0, 2, I guess. But 1, 1 is in here. But 2, 1 isn't. Right, 2, 1 is just outside, because it's directly above this one, and therefore outside the circle. And likewise, 1, 2. And then we just go around and go, okay, well, all these symmetrical points are also in it. So how many is that? Well, that's going to be, in total, 13, I believe. 9 inside, and then 4 on the edges. Right. So n is 13. So what's the amount we have to increase the radius by to get, well, n is 13, so 2 times that's 26, minus 5 is 21. So we need 8 more grid points. Now, the most obvious ones that are closest to the circle are the ones I mentioned at 2, 1 and 1, 2. And all these symmetrical ones at 2, minus 1, and so on all the way around. And it just happens that there are 8 of those, right? There are 8 of those that are quite close, equally far apart, because all these radii are symmetrical, right? So equally far away from the origin. So we just need to increase the circle by an amount such that we go through all of these. And we won't go through any other points, I don't think, because the next point along is like 3, 0, or 0, 3, or whatever. So we just need to increase the radius of the circle just to hit all of these 8 coordinates, and then we'll go from 13 to 21 in total. Now, okay, this coordinate here is 2, 1, of course, so it's a distance of 2 squared plus 1 squared is 5, so root 5 away. The radius is currently 2, so we just need to increase it by root 5 minus 2, that little amount there, root 5 minus the current radius 2, to increase and to get all of those 8 points that we're missing. Really interesting question. Don't be afraid of the questions that you haven't really experienced before, because as long as you think it through, draw a picture, of course, because I'll never stop talking about that. It shouldn't be too hard to figure out. Another interesting one here that is also something that you've probably never seen before, that I'm also going to have a picture to help me with. We've got things starting at 0, and we can either go 1, 2, sorry, this is probably more like 2, 1, or 1, 2. Those are the two kind of actions we can take. And we're trying to get as close as 25, 75 as possible. Now, the obvious thing to check is, can we go through this? So can some number of this vector plus another number of this vector get us to here? Well, okay, we can combine these vectors to make this, and then we can say the top bit needs to be 25 and the bottom bit needs to be 75, and solve this. And of course, we need m and n to be positive whole numbers here, because we're doing a positive number of those and a number of those. So do we get positive whole number solutions here? We'll double this one up to get 4 plus 2 equals 50, and then take away to get 3 cancels is minus 25. And of course, n is neither positive nor integer here. So we definitely can't reach this point here by any combination with a positive integer number of movements, which is what we need. So that doesn't work. So let's rethink this again and draw it. Now, let's think about this carefully. 2, 1 is kind of off in this direction here and has a gradient of a half, right? Because every 2 you go across, you go up 1. So this is just lots of the vector 2, 1. So imagine doing it once and then again, 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 and we just go off in this direction. 1, 2 is across 1 up 2. So it's much steeper, has a gradient of 2 actually. And you just sort of go off in this direction, following the line y equals 2x. Now, where is this? Well, it's 1 across 3 up every time, right? So it's actually steeper than this one. It's up here somewhere. Right, that's where it is. Which is really interesting because it means that to get as close as possible to this vector, you don't want to take any of these. Sorry, to this position. You don't want to take any of these vectors. You just want to take a bunch of these. Any of these that you take will bring you further away from here. So we just want to do a bunch of these and get as close as possible. Now, how do we get as close as possible? As mentioned, this is the line y equals 2x because it goes to the origin, it has gradient 2, 1 across 2 up every time. How do we get as close as possible? Well, there's a bunch of ways you can do this. I just decided to say, well, let's make a perpendicular line here, and let's look for this coordinate. This line has gradient -1/2 because it's perpendicular to this gradient of 2, and goes through this point here. So this black line is this equation, but goes through this point. So we just shove in x is 25, y is 75, and we can solve this. This isn't the most efficient way of doing this, by the way, but I get this. That's the equation of this line. And then I looked for the intersection of that line and this line, by setting them equal to each other, and then I doubled everything and solved that, and I got x is 35. So this coordinate is 35. Of course, then double 35 is 70, because you just double the x coordinate. And now I can just find the distance between this coordinate 35, 70 and this coordinate. X distance is 10 across, y distance is 5 up. So it's 10 squared plus 5 squared is the distance squared. And we get 125 root of that. Of course, you've probably done enough simplifying surds to recognize immediately this is 5 root 5, and that'll be my answer. Really interesting question. Again, a sketch massively helped me. People who watched a lot of my Tuamura videos will have had enough of me talking about how much you have to sketch things, but I never will. Cool. Another question where a sketch helped me. Excellent. What a surprise. So the first thing I thought was, okay, why don't we just set this equal to this? So root this to get plus minus root x. Set this equal to this and look for discriminant of 0, because that will be meeting at a single point. The problem is when you do this, I also sketched it, of course. We've got a parabola with y-intersect of c, and we've got a plus minus root x. So notice the subtle difference between this graph and the graph we saw in the first question. Because this is y squared equals x, you can put in x coordinates that are positive, and you'll get 2 y coordinates out for each, because like -5 as a y coordinate will square to the same thing that +5 did. So we end up with a graph that looks a bit like this, which is interesting. And we want these to meet at one point, so we want to lower c to a point where this graph just kind of touches the other one. So okay, yeah, set this equal to this and look for discriminant of 0. Except when you square this to get rid of the root x, you're going to end up with a quartic, not a quadratic, which is, and it's not a nice quartic. It's not a quartic that I can just write in terms of something squared because of this term, which messes everything up. Otherwise, I could make some substitution, but this just isn't going well at all. So you have to put your thinking cap on and find a different way of doing this. And the way to do it is really interesting. Again, draw it. I'm only going to draw the top half this time because I don't actually care about the bottom half because it's irrelevant. So just draw the top half. Now, what can we say if we move c down far enough to make these curves just touch at one point? What can I say about them? Well, this is a massive hint, because what it's saying is this graph, the quadratic, and this graph have the same gradient at the point that they meet. Right? They're meeting tangentially, so they share a tangent. So they have the same gradient at the point that they meet. So if I differentiate this one to get 2x, and differentiate this one to get a half x to the minus a half, the gradients of these two curves here is the same at this meeting point. So therefore, this gradient is equal to this gradient at that x coordinate, which is this. So I can set them equal, and this is really weird. I've done a lot of maths, but I've never actually set two differentials equal to each other quite like this. But it's a really fun little method. Times everything by x to the power of a half to clean out this. Divide by 2. And then raise everything to the power of 2 over 3. If I raise everything to the power of 2 over 3, 2 over 3 times 3 over 2 cancels, so you just get x equals, and then this. So this is the x coordinate of the point where the two curves meet. And now actually you can look up here, and this is implying that you need to take the cube root of 4 at some point, and the only answer with a cube root of 4 in it is b. So actually you can circle the answer b fairly confidently to this and move on. But just for sake of completion, let's continue. What we need to say is, okay, well, that's the x coordinate of the meeting point. So, okay, what's the y coordinate of this curve? Well, it's the x coordinate squared plus c. So this coordinate is this. It's this coordinate squared, and you just raise this to the power 2, and so 2/3 times 2 is 4/3, and then add c. But it also this coordinate is when you put this x coordinate into this curve. So you say it's going to be root. It's just the plus bit, isn't it? It's root this, and again raise that to the power of half because that's a root, and then 2/3 times a half is just 1/3. Which means that this coordinate here, the y coordinate from this curve, is the same as the y coordinate from this curve. So this thing is equal to this thing. We can take that away, and we get this. Probably a few ways to do this. I factorized out a quarter to the power third from both to leave behind 1 from the first term because it's just itself, minus this, because of course this is a quarter to the power 1 times this, add the indices together to get this. Of course this is just 3/4, and when you cube root a fraction, which is what this is, you just cube root the top and bottom separately. Cube root of 1 is just 1, cube root of 4 is cube root of 4, and we get this answer here, which is what they wanted us to get. Really interesting question, probably the most interesting thing on this paper, I thought. That method was just really, really nice. This is the hardest question on the paper, I think, at least for the first 10 questions. There's a very, very nice little kind of thing that you have to spot here, which is that they've given you a circle and they've given you this area S and T. The thing is though, you can move this point around to just say you dragged this over to here and said this was the area S. But notice how you could drag this further and further, and you could make S arbitrarily small. And likewise you could drag it the other way and make it arbitrarily small the other way, and you could also do the same to T. Right? You could drag this point around and make T very small if you just kept going and going. So you can make our S and T arbitrarily small, and also you can make them arbitrarily large in comparison to the other, because you could drag C at this point here all the way along to here to make S basically 0, and then you could make the circle really, really big to make T really, really big, whilst keeping S basically 0. So you can make them arbitrarily large kind of relative to each other. And what this kind of implies is that the entire picture is completely pointless. Right? We can just make S and T whatever we want to, small or large. And all we're looking at is this algebra here and trying to minimize this algebra here. Right? The picture is irrelevant. There are no constraints provided by the picture. We just need to look at this algebra and try and minimize it. Now the first thing I thought was to break the fraction apart in the middle, to say it's this over this plus this over this, because of course if you were to simplify this you would just say same denominator, put them together, get this. Okay, and now we can just cancel some s's and cancel some t's, and this is, I didn't really know what I was doing with this. So what I decided to say was, I decided to say, well if s is equal to t, and I know it can't be, but if s was equal to t, you would just cancel this, you get 4/5 plus a fifth, which is 1. Okay, so I know the minimum isn't this, probably, even though I know s can't be equal to t, but I can very easily get 1 out of this. Can I get something smaller? Well, let's just set s equal to a half t, and plug that in. Right, and this half drops down there to make 4/10, the t's cancel. This half comes up to here to make a 2, and the t's cancel to get 2/5. Now, of course, 4/10 is just 2/5, plus 2/5 is 4/5. So I've made 4/5 here. So by choosing s is equal to half t, I've made this one. So now the question is, by choosing different things, can I make anything smaller, or is that the minimum? Now it seems unlikely to be the minimum because it's basically the first thing I tried. But let's just now set x equal to be 1/3 of t, and see whether we get something smaller or bigger. Right? Now notice, when you change s, when you make s smaller, which is essentially what I've done here, this fraction becomes smaller because the numerator is smaller, but this one becomes bigger because when you divide by a smaller number, you get something bigger. So it's not obvious whether or not this will make this smaller or bigger in total. So let's just try it. Let's put in 1/3 t. I'll do it a bit quicker here. The third will drop down to here to make a 15, and the 3 will jump up to the top to be here. Of course, this is 9/15 makes 13/15, and that's bigger than 4/5. So by making s smaller relative to t, I've actually made the total thing bigger, which is interesting, which actually suggests this might be the minimum. But I need to go the other way. I need to make s bigger relative to t. So let's make it 2/3 of t maybe. Again, put the things in, and you end up with this, which again is bigger than 4/5. When you simplify this, you get something bigger than 4/5. So I'm fairly confident that this is the lowest I can make, because I've gone either side of the two. Now it's possible the minimum is like, I tried 1/3 and 2/3. It's possible the minimum is like at 60% of t, but it seems unlikely. it seems unlikely to be able to drop all the way down to 3/5. So I'm fairly confident my answer of 4/5. But also, of course, there's some very intelligent algebra you can do to prove this, which I'll do next. But of course, when I was actually taking this paper, I just circled this with sort of a high degree of confidence and moved on. But to do this properly, what you can do is you can do something really fun. You can make u equal to s over t. So make this substitution u is equal to s over t. And put that in. Now t over s is of course 1 over u, because you flip these over, which is u to the power minus 1. And now you have this new function of u that you want to minimize. So of course, talking about a minimum, differentiate. So differentiate this to get this. And now you want the minimum value, so you set the derivative to be 0. And you solve. You can times everything by 5 at this point. What to the power minus 2 equals 4? Well, that's going to be a half because you square it and flip it over. Square it for a quarter, flip it over for 4. And you get u as a half, but u was this, so s over t is a half. And you can cross out the t, and you get s is a half t. So it's a minimum when s is a half t, which is my first guess. And that gave the answer of 4/5, as I found out earlier. So that's the little proof of that. But again, in multiple choice questions, you don't often need to find these really intelligent pieces of maths. It is really nice to, and this is a really cool piece of maths, but you don't need to. You can figure it out using other resourceful measures if you want to. This question is really interesting. By far the cleanest way of doing this is to look at these numbers 4, 6, 4 and think, is there a place in maths, particularly where I've seen 1, 4, 6, 4, 1 before? And I hope there is. It's in binomial expansion, right? When you're expanding with a power 4, you get these coefficients 1, 4, 6, 4, 1. So by the symmetry of these numbers, I think that there's a binomial expansion hidden in here. How do I get an x to the 8 and a y to the 4? Well, okay, putting a y here would make the y to the 4 and y cubes and y squares and y's. That's good. Now, putting an x to the 2 at the front would give me x to the 2 to the power 4 is x to the power 8. And that would give me all of these powers as well. So I think this bit here is x squared plus y, all to the power 4, and then all squared equals 1. But of course I can multiply those out, and then I can take the 8th root, and of course minus 1 to the power 8 or plus 1 to the power 8 is 1. So that's that. And now of course this is now two graphs. It's either this graph, rearranged, so just taking away x squared from both sides and having a plus 1, or it's this graph where you have a minus 1 instead. And this is two upside down quadratics, one with a y-intercept of 1 and one with minus 1, which I think looks like this graph here. So just a really nice little spot there. Look for these ideas of symmetry with these alternating powers and these Pascal's triangle coefficients. If you ever see those, do try and reverse engineer some kind of expansion. Going to be by far the easiest way to get it done. Last one that we'll do then. So we've got a really interesting way of making a curve here. Two polynomials where you plug in x and you plug in y. The same polynomial twice, I should say, equals 0. Which of these can we make? Well, let's just try the simplest polynomial we can think of, which is probably not the simplest actually, but p of z equals z. That's a very simple polynomial, where you just got a function, you plug in the number, and you just get the thing itself. That's a polynomial because it's to the power 1. So of course p of x is going to be equal to x, and p of y is going to be equal to y. So we get this when we plug it into here. But of course, rearranging, we get this, which is this graph here, right? So we can definitely make d. So it's not b and it's not e. What about the others? Now, what's the next easiest polynomial? What about z squared? Right. So p of x is going to be x squared, p of y is going to be y squared, and we get this. Now that's interesting because that's a circle centered at the origin, radius 0, which isn't really a thing. It's nearly this, and I think I can fix it. I think how do you get a number here? Like how can you do that? Well, what if you just took away 1 from this? And then said, okay, p of x is x squared minus 1, p of y is y squared minus 1, this is a minus 2, added to that side, and we get this, which is a circle radius root 2. So I can make this as well. So I can make c and d, so the answer is either going to be d or c, depending on whether I can make a. Now, a looks like a quadratic, right? Y equals x squared plus c for some value c. But the thing is, notice every time I've done this, the x and the y powers have been the same in the end. And that's very logical, because you're using the same polynomial twice. So how are you going to get x squareds and just single y's when you do this? Well, the thing is, you can't, right? If you're using the same polynomial twice, regardless of whether it's a cubic or a quadratic, and you're just plugging in x's for one of them and y's for the other, you're going to end up with something completely symmetrical around y and x that have the same powers, right? So we can't make this. There's no way to make this. And thankfully, I don't even need to think about this because both options were not B's. So the answer is going to be C, and that's the end of the paper. Thank you for watching, and I'll see you next time.